All right, so to go over some of the news and updates, problem set 5 is now due on Gradescope. So hopefully you guys have turned that in. I posted a reaction strategy summary thing similar to the past few topics in topic 4 handout folder. Before the final, I'm going to try to get these sorts of things done for the earlier topics as well, so you can have that to refer to. It's a matter of amount of time I have and whether to make an exam first or do that after. I'll probably make the exam 5 first before I start working on that. Office hours this week are on Wednesday and Thursday, so there won't be office hours today or tomorrow. This is so that it's a little closer to the exam, so that I think that'll be a bit more useful. I also want to say thank you for the people who have given some feedback on. Will you post a solution to the practice? Yeah. So exam 5 practice, solutions to problem set 5, and extra problems will go online at Canvas at 7 p.m. So I actually already have that in the folder. As soon as it hits 7, it should appear. With the problem set in extra problems will be in the problem set folder, and exam 5 practice will be in the exam 5 folder. So those things should be up soon. I just wanted to, give people a bit more time to try it on their own, and having them all go up together at the same time as problem set 5. Hopefully all of those are in by then as well. But thank you for people who sent feedback on the quiz. I sent an email out. It was kind of long over the weekend where I addressed some of the common things I saw on the early submissions. I saw a lot of these same sort of issues reiterated in some of the later submissions as well. So I think these are hitting on some of the key problems. There was a number of people that were concerned with technological issues preventing them from being able to get to an exam or submit an exam on time. I would say if this happens, please don't panic. I understand. Feel free to just let me know after the fact. This happened on the last exam with several people, and there were no penalties applied. I would say please don't abuse this. If you're sitting there and everything's frozen, or like your internet stopped, I would just say maybe take a picture of your exam as evidence that it was done at a certain time, and that will, I guess, add a bit of honesty to the practice. If it's like 5 minutes after, I wouldn't waste time trying to take pictures. I would just upload it, and it won't be a big deal at all. So hopefully that alleviates some of those issues. If someone's having a lot of consistent problems like this, where your internet is a little uncertain, feel free to email me ahead of time just so that I'm aware. That way, I guess there's a bit of added knowledge on my end of your situation, just so I know it might be coming. A lot of people, because of these technological problems, they wanted even more time to finish the exam. I kind of explained in the email the balance of two different sides I had to work from. If I make it much, much longer, then the exam will need to change. And I think that would be probably a detriment to the students, as you wouldn't be as prepared for the types of questions that are coming. But I think hopefully with the knowledge that if there's a technological problem, you will not be penalized. These things will be just fine. Hopefully that alleviates some of them. And the current exam, I am making the exams shorter so that you will have more time to do them and get everything processed. Of the balance of those two, I think I'm still weighing in on the right one for the most people. I know this doesn't address everyone, but at the end it's just a hard situation to be in. There was a number of people who noted concerns about the final exam. So that will be a bit more relaxed in terms of, I think, the exam experience. I usually design these to be twice as long as a normal exam is. So in this case, if I'm making exams that are about 45 minutes long, you would have about, in principle, 90-minute exam for the final, and you have 3 hours to take the final. So hopefully, people who have had some additional concerns with completing it or potential problems, that shouldn't be as much of a problem on the final. I will go to an open note format for exam 5 in the final. There's a lot of good reasons to do this. I won't change the exams very much. I think you guys still get the same full-length exam finals period. To my knowledge, none of that has changed. We'd be taking the final at the same time as we normally would, and that is a 3-hour window. I think for the average student, that this should be that's the knowledge that I have at the moment, and I don't think that's going to change because they didn't change the time of the finals, and that's why we had a truncated semester. Um, but yeah, we will go to open notes. This will not change the difficulty much. The only thing that I would be removing is what is the pKa of something, or what is this functional group, because that is something that's very easily referenced, and I think take some of that element out. So instead, there would just be another question that you might have to maybe consider a bit more. I don't intend for this to make the exam a lot longer either, so there's going to be a balance to the type of question it'll be. But I'd say it should all look fairly familiar and won't come as any shock. My plan is to have minimal changes, if at all, with the exception of maybe removing a few of those problems. There have been many exams and many assignments, and I have felt this on the creation and grading side as well. This was not an ideal situation to be in, but just so that we could still have the same amount of points and we didn't have an uneven weight to the class. This is something that Georgia Tech and I think all of the system of Georgia put an emphasis on, is to try to maintain some of this same core structure, or not changing the way the syllabus is essentially arranged in terms of point distribution, where some assignments now would be counting for a lot more potentially in a stressful period. I think that the backside of that is it creates more frequent assignments, even if they're shorter or covering less material. That still is, I think, having maybe an impact. So I'm sorry if you are having some of these feelings. We're trying to come up with the best solutions we can right now. And for extra credit, I didn't want to give extra credit across the board because not everyone is impacted evenly. And I have a proposal to try to address this somewhat, because I think there are some people from the feedback that are having more struggles with either the situation, whether it's technological or otherwise, that I would like to try to accommodate. On Wednesday, I think I'll be able to talk more about that. I wanted to talk to some colleagues to get their opinion, just to make sure it would be implemented in a fairly consistent and fair way. And I'll let you know more about that. But in case you're in one of those positions, I'll have at least something to offer. I don't know if it'll be enough to fully balance it out. It's hard to gauge what that is tangibly. But I'm coming up with something, and I'll get your thoughts on it. Are there any questions on some of these changes, or anything else people want to bring up right now about either the function or of Exam 5 or the final, or anything like that? All right. And if you still want to give some feedback, the quiz is still up. I'll still check those periodically to see what people are saying. I know some more came in this morning that I haven't had a chance to look at. So I'll go through those later today. All right. So now I guess we can go to the sort of lecture review. So our last lecture was lecture 30, and it was our last one, which could be a sad face or a happy face, depending on your thoughts on the class. And we covered, it was a little shorter than the average lecture, and I intended this just that we got through most of the material beforehand, so there wasn't a whole lot more material you hadn't seen that we could cover on the problem sets. And these included the Osito, acetic acid, and Malonic ester synthesis. All right, thank you very much. And so these are essentially two variants of the exact same process. This is where we have either an acetoacetic ester, where X would be like a methyl instead of an alkyl, or if you have two esters, it's a malonate. And these types of malonates that are very acidic can be alkylated either once selectively, or you can add in two equivalents to either add in two of the same or two different alkyl groups. And then you hydrolyze the ester to turn it into a carboxylic acid and heat it up. And it goes through this cyclic transition state where you can lose carbon dioxide all at once. You go to the enol, and then after tautomerization, you get back either a carboxylic acid or a ketone. Someone asked me about this general bigger picture visualization. I will go over this in a second because it was posted on Piazza, and I have it on the next slide to maybe draw it out a little bit more and explain further. We learned about reactions of enamines. So enamines we learned how to make in a previous topic, but we didn't really do much with them. So these are very nucleophilic pi bonds. They're kind of intermediate between an enol that's neutral. This is more nucleophilic than an enol, but it's less nucleophilic than an enolate that would be negatively charged. And these are able to react with primary alkyl halides that are usually very reactive alkyl halides. And we have the lone pair from the nitrogen going down, pushing through the bond. These are similar arrows to what you saw in topic 2 with electron-rich aromatic ring systems. And then water is able to come in and hydrolyze this intermediate after the reaction in our normal hydrolysis of an enamine or iminium mechanism that gets us back to a ketone. So the overall process here is actually just alkylation of a ketone. I would say for you guys in class wondering when do I use this, it'll mainly be if I ask you about enamine reactivity. Most of the time you would just be able to take something like acetone, react it with LDA first to make the enolate, and then add in your alkyl halide, and this would achieve the same overall goal. But there's a lot of elements of sort of reactivity. That's good to talk about. So this is sort of the Piazza question. Can we draw a detailed mechanism for this reaction? Which reaction? The enolate or the hydrolysis? For the enamine reaction. So you want the formation of an enamine? Have I not uploaded the Lecture 30 video slides to Canvas yet? If I have not done that, I apologize. I should have uploaded that with the video because I make them as I make the video. I will address this in real time, the whole mechanism, but not detailed. Okay, after I address sort of the bigger picture of the malonate ester synthesis, I will go back and put that in. There is no Lecture 30 video notes. I sincerely apologize. I just need to pull this from my iPad and send it to you guys. I will do this after class. I'm sorry, if there's something that I should have uploaded, feel free to email me and let me know. I guess right now we're kind of towards the end of the class where that's would be an issue. But right now I have many different things that I have to remember to upload, and I thought I did that right after I made the video. So for this, I use these sort of things like I say they're a theoretical dianion equivalent. So sometimes when you have many reaction steps, right, because we're doing alkylation, we have a hydrolysis that we heat it to decarboxylate it. Sometimes you lose the bigger picture of what did we do overall in the transformation. And a lot of times organic chemists use a term called like a synthon. It means this is sort of like an abbreviated view of what this process does. And so in effect, using something like an acetoacetic acid ester, or acetoacetic ester, the overall process in this reaction essentially turns this molecule into an acetone dianion, where you put the anion on the same carbon. So we were able to do sequential alkylations where one of these anions would react with a bromide, an alkyl bromide, and another one would react with a second alkyl bromide, and this would be your final product. So sometimes these sort of bigger picture views are useful in retrosynthesis, or if you're doing a synthesis problem, it's like, okay, somehow I need to put two different R groups onto a single carbon of acetone. Like, how would I do that? Oh, I can't use LDA because the second reaction would not work. So let's imagine we try to do our LDA trick here, right? So if we have LDA and then let's say R1X. So we're going to end up getting this molecule. If you try to use LDA again, it's actually going to go to the other side. So there is utility to these beyond that you can make products you cannot make using the LDA process. So this is just sort of a representation of the bigger, higher level view of what this chemistry is doing. And at the same time, you could do the same thing. Now the malonates are an acetic acid dianion, because now these are going to be able to react with two different sequential esters. Of course, this molecule cannot exist. You would not be able to have an enolate in the presence of a carboxylic acid. So this is mainly just to be viewed as a overview equivalent. So hopefully that explains this a bit. All right, and I can go through this reaction, this enamine reaction, maybe a bit more explicitly. Oh, actually, I'm gonna erase some of this extra stuff because it might get in the way of what I'm saying. All right. So there's a few things that are always going on with enamine reactions. We always have this amine and a little bit of acid. So these are going to be able to react first. So we want to think about having most of the amine as this basic amine. And there is a little bit of acid around, so we're going to have protons available. We're going to have a little bit of salt, and this will kind of act as a proton transfer catalyst. It'll be able to help protonate something and deprotonate something as needed. So then we can have another equilibrium between the secondary amine and the ketone. So this will be able to attack the ketone. This gives us an initially zwitterionic intermediate. But with the help of our proton transfer catalyst coming around, we'll be able to protonate and deprotonate this. So we can just say proton transfer. We're eventually going to go and make the alcohol a good leaving group. And we'll have this lone pair on the nitrogen that can go and kick it out. Whenever we have iminiums in this form, the alpha hydrogen, so this is analogous to like a ketone in some ways, only now this hydrogen is going to be even more acidic than a ketone. This is actually way more acidic than ketone, because in a ketone you deprotonate alpha to a carbonyl and it goes to put the negative charge on an oxygen. Now we're able to have a base come around, and this very likely could be another molecule of the amine, and its conjugate base becomes neutral, so this is actually going to be even more favorable. And this is how we get to a neutral enamine molecule. That was an ugly bond. So now this is something that you would first make in a reaction, and then in a second step we would add the alkyl halide. How do I get rid of this? Oh, there it is. So now we're going to add in an alkyl halide. Let's say we're going to use, we'll keep it simple. Let's say we'll use methyl iodide. So similar to enols and enolates, enamines are nucleophilic at carbon. We're going to have the electrons from nitrogen come down, push electron density into the double bond to do an attack on the methyl iodide. This gives us an iminium once more. It would have an iodide counter ion. we've added on the methyl. And then on the workup procedure, this could have gone back to an enamine briefly. A lot of times in the second step, we don't have a lot of protons around to do these extra proton transfers again. So we just add water afterwards, and this would end up hydrolyzing it before getting any other unwanted alkylation reactions. And this will go through the same process and it'll essentially be the backwards process of what we did at the beginning. Because note that there's strong similarities between these two intermediates. They essentially look the same. We're just going to do the mechanism now in reverse. We're going to have proton transfers to now make the amine a good leaving group. Oh, there's no lone pairs on that. And finally, it could be water or the amine. Since we just kicked out the amine, it makes sense that maybe you'd have the amine come in. And the alkylated group would be your product. So there are a lot of steps that go into this. And that's why hopefully we remember how to make an amine or enamine. And in general, whenever you see the mixture of, say, a ketone plus a secondary amine, we want to immediately be thinking that there's two things that are in solution. We potentially have reactive iminiums around, and these will also be in equilibrium with nucleophilic enamines. So in the case of something like the manic reaction, we have nucleophiles attacking an aminium like this. That's almost always made from formaldehyde, though, rather than acetone. Does that help to clarify enamine alkylation chemistry, the beginning and the end? Cool. No other questions on Piazza right now. Are there any other questions about anything right now? Someone want me to go over the practice exam some? We can start talking about that. If you have questions about that, I can answer those here. Yes, all right. Let's do that then. Sure. Is there a specific question, or you just want me to pull it up and see where we 12F. Let's go look at 12F. So I have it all filled out with already some commentary on it. So I'm going to use that to go from. Oh, 12F. This is a good one. People last year on the exam did not like this one very much. I think this is one of the extra practice problems. We can do 13 too. We can talk about E. We'll talk about whatever we have time for right now. But I'll copy this over here. So for 12F, we have this molecule. And I think this one just gets a little difficult because it requires you to number and keep track of some of the enolates. So if we have sodium ethoxide around, we can imagine deprotonating the ketone. So it turns out, no matter where you deprotonate, it effectively makes the same ketone. This molecule has elements of symmetry in it, where we end up having... Oh no, there's still different ones. I apologize. There's two main enolates that you can consider that I will draw. You could either draw this enolate or this enolate. They would be redundant on the other side of the molecule because there is some symmetry. So I'll draw the different protons I just took away. We could either make deprotonate here, or we can imagine deprotonating here. These other two hydrogens are actually the same thing. So now we want to consider, can we do a reaction intramolecularly with either of these enolates? So if we go and start numbering, we know that the enolate on the right, it's going to be nucleophilic at carbon. This would be 1, 2, 3, 4. If we tried to have these electrons push down and attack this carbonyl, this would make a 4-membered ring. And this is bad, or at least it would be strained and it wouldn't go forward. If we look at an alternative, though, we could now have this other enolate. I'm going to put this in green because it's the good one. This would be a 1, 2, 3, 4, 5, 6. You can actually count from the other side of the ring as well. It'll make a 6-membered ring too. So along the way, we're going to actually make 2 6-membered rings. If we have these electrons come down and then attack here and go up. So if we try to keep track of the 2 different rings that we make, maybe I will count from this direction too, just to show that we're going to make 2 different 6-membered rings. And when we do that, we'll get to this intermediate shown here. So you have to shift the rings around a little bit to get the right orientation. You'd end up with a ketone on the right, and this one rotates over, and it makes this alkoxide. The rest of it ends up being pretty similar proton transfer to protonate this alkoxide, and then a deprotonation to make the enolate, so proton transfer overall. And then we have the E1CB elimination to give us the product. So usually whenever I number, I'll start at the enolate carbon. So this is the one that's attacking, and that'll tell me where the it'll give me information about sort of this bond that I make right there. Actually, I did you can also start going from the ketone. It's usually the same. Maybe I mix it up. As long as you're consistent, you could start from probably the ketone or the enolate carbon. I realized I probably numbered the other direction, but usually you want to have the 2 ends that react and start at one of those. I would say try to practice and find a way that works well for you. As long as you can keep track of the carbons, things will work out. But I would definitely try to start at either the ketone or the carbonyl that gets attacked, or the carbon of the enolate that is going to be attacking. And then you should be fine. This is called a transannular reaction because it's attacking across a ring. And I probably won't put any of these on the test because I think they're a little too hard to figure out in a short period of time. But the other cyclization reactions, I think, are a bit more straightforward. They don't require quite as much spatial evaluation. Yeah, these are tricky. I think this is one of the recommended problems in the back of the book, so I threw it in, and I think I curved the exam based off of this question alone. But I thought it was a good practice problem for a practice test for sure. There's so much to learn. All right, we were going to pick another problem to go look at. Number 13 on the practice exam. All right, I have this all written out. So I can just go talk through it. So in the beginning, we see a malonate, and I'll make a line. Oops. We have a malonate. This is number 13. With sodium methoxide, and we have an aldehyde. So if we look at the different reactions that can take place, sodium methoxide could add into the aldehyde, but that would be reversible. And so the best option is just to use it as a base to deprotonate the malonate. So this is a case where, in looking at the product, it can be like, oh my goodness, what in the world happened? But if you start going and pushing your arrows and doing thinking about this problem more in the sense of reactions that we've learned, it quickly kind of comes together. So usually when you see an aldehyde and some sort of 1,3-dicarbonyl, this would be like the Canova-Nagel condensation. We'd expect to actually just go and stop at this first intermediate. This involves methoxide deprotonating. The enolate of dimethylmalonate attacks formaldehyde. We can have proton transfers to protonate this alcohol and deprotonate the hydrogen between the 1,3-dicarbonyl. And we have the E1CB elimination to give us what would be a normal Canova-Nagel product. So now the challenge is, how in the world did this extra molecule get attached? And the other thing we know about malonates are that they are soft nucleophiles. So these like to add. So in the case of 1,3-dicarbonyls, this is the situation when these hydrogens are so acidic, they will always eliminate. So if it's a simple ketone, they're much less acidic, and we need to have heat to get enough of the enolate to form to eliminate. In this case, this is very acidic, so we're going to completely make this anion, and there's no stopping it from kicking out hydroxide. And so now we have a Michael acceptor that turns out to be very reactive because it's not very hindered. And this is why we end up seeing 2 additions of the malonate adding in. Then we're able to have electrons flow down. The carbon of the enolate attacks the 4 position of the malonate. And then we just have a final protonation to give us the product. Hopefully that clarifies or demystifies this problem a bit. I would say this exam is a little harder than what the exam I will make. But practicing with harder questions is usually a good thing for a practice exam, I think. Cool. All right, next up. So then we have a question on 12E and a question on number 2. Cool, that's where we are right now. So I'll go get 12E. So this one is somewhat related. Oh, so for this case, this is just in general. Usually, when we have soft nucleophiles, these will do 1,4 additions. And so this one is the 1, 2, 3. It's attacking the 4 position of the alpha beta unsaturated carbonyl compound. In general, you wouldn't have much of a choice because malonate enolates are not reactive enough to attack an ester. That requires more energy. And that's why they usually stop in a lot of the beta keto ester or 1,3-dicarbonyl syntheses. We always have that deprotonation step as the last step that kind of stops everything and makes it drive to one of the preferred products. But here we have, in this next question, 12e, we have a carbonyl compound, and a nitrile is also a good electron withdrawing group. So this will also make this central hydrogen very, very acidic. In a lot of ways, this will be the same as our 1,3-dicarbonyl series. In the previous section, I talked, or I removed a bit more on these types of molecules. I think we only had one example that kind of used them in our notes this time, so I probably wouldn't be putting a nitrile on an exam, but they react essentially the same as any sort of our 1,3-dicarbonyls. So this would be a Canova-Nagel condensation, where we have had this add into a carbonyl and also do the E1CB. This would be like aldol plus E1CB. And so if we're making this enolate anion in the reaction conditions, we would want this to be able to attack into an aldehyde. So we need to look at this molecule and imagine that this is going to be our nucleophile, so this needs to be our electrophile of some sort. And that ends up being an aldehyde for that purpose. Got a question on number 2. The question is, for 2, I thought ester enolates are more nucleophilic than ketone or aldehyde enolates. Why wouldn't it be D? So I have notes written out on it, so I'll make it a little bigger to see if we can read them. So the ones that are in an enol form is similar to essentially which one would be the most acidic. And things that are more acidic end up being less nucleophilic. Because in the process of going to the enol, we lose. So from ketone, I'll say keto since it's more general, to enol, you lose the carbon-oxygen double bond. And this is usually the thermodynamic. Enols are nucleophilic. And so from that perspective, the ones that will exist in an enol the most would be the ones that have probably the most stable enol. And if we compare, this orange is we need to switch it up. Let's go back to blue. So if we consider this enol, this has a lot of things going for it, and it's able to overcome losing one of the carbonyls, carbon-oxygen double bond strength, because we gain a resonance interaction of this lone pair flowing all the way into this carbonyl system. And we also gain hydrogen bonding. And so if we compare it to something like the enol of dimethylmalonate, not only did this lose its carbonyl, it's additionally losing the resonance of this methoxy group into that carbonyl. While it does still have another carbonyl to add in through this end, now it's being shared as well with this oxygen here. And whenever we have two oxygens trying to share the same carbonyl, neither one's is happy. They want their own carbonyl. And so previously, I'll zoom in over here some more. I was writing pretty small, I guess. This is the general idea. Previously, in its ground state, it has this resonance interaction, which makes it lower in energy. Whenever it goes to its enol form, this lone pair loses its resonance with its old carbonyl, which actually makes it less favorable. And so in all these types of, I think the prediction of what is going to be in the most enol form generally correlates very well with what is the most acidic too. So the resonance that we lost was this resonance interaction here, is this one. Because now these are no longer in conjugation with each other. And if you try to think that like, oh, well, it can still have resonance with another carbonyl over here, it's actually competing for resonance with the other oxygen on the other side, so it's not as strong as a stabilizing effect. I'm trying to think. I believe all of these do correlate almost directly with acidity, if that helps to sort of put these into categories. And usually the things you want to remember are that esters are less acidic than ketones and aldehydes, and esters have even less enol form than ketones and aldehydes. Are there any other questions on the practice exam you want me to comment on a bit more right now? Number 1. Now we're looking for the one that's the least acidic. I think we asked what is the most acidic one on your problem set. May have been these same molecules. So right off the bat, something I think hopefully we can all see is that the ones that will be the most acidic are the ones that all have hydrogens in the middle of two carbonyls. This always greatly increases acidity. So we'd want to go and immediately disregard A, C, and E from being options, because then it will get us down to either B or D, which just have a single carbonyl to stabilize the conjugate base. So if we still use the rationale of things that are good acids, we'll have stable conjugate bases. We're going to be comparing two different enolates. And this is where it gets a little trickier to rationalize. Because both these look like they have a resonance structure that can move the electrons onto a single carbon. So these look fairly similar. This should not be a resonance arrow. This would be a equilibrium arrow. And here we have an enolate with, again, acyl carbon. So we don't have additional resonance to try to explain them. The difference comes from the ground state energies getting to these reactive states. So the ester enolate ends up being even more nucleophilic and more reactive because it also has an additional electron donating group that can go and imagine attacking, putting negative charge on that oxygen. This is a poorer resonance structure, but technically is still a valid one and does help to explain the increased nucleophilicity. We usually don't want to make resonance structures with multiple positives and negatives, but this helps to think about the nucleophilicity. And the other thing is the ground state structures that these had. And the ground state, going from the ground state to the enolate, we lose this very nice resonance interaction of this lone pair donating into the carbonyl. So this will lower the ground state of the molecule. So trying to deprotonate it, you have to break that extra stabilization energy. And that's what makes this harder to deprotonate, and this is why in general esters are harder to deprotonate. And it's a similar logic for the stability of their enol forms. Previously they had this extra resonance interaction that normal ketones don't have. And so whenever you deprotonate it, this is more stabilization energy you have to break and overcome. Cool. Any other questions? If not, we can call it a day. I will make sure to upload the video lecture notes ASAP on Canvas. I'm sorry that I overlooked that earlier. I'll get those uploaded. I'll upload this video as soon as it gets processed and comes to me, and I'll upload these in-class notes as well. Everyone have a good one.